This problem is asking us to sketch a couple of curves and find the area of the shaded region that's formed. So we'll start by graphing this parabola. Be careful with the y-axis here. Notice the scale is counting by 2. And there's our curve. We also have y equals 0 and x equals 4, creating this somewhat triangular region, not quite triangular. We can calculate its area using definite integral. It's going to be from 0 to 4 of 1/2 x squared. The antiderivative of that is 1/6 x to the third, again from 0 to 4, and plugging 4 into that we get 64 over 6, or 32 over 3. So there's the area of our shaded region. Next question asks us to imagine the shape and try and sketch it if we were to take this region and rotate it around the x-axis. So when it shows up here below the x-axis, we know it's going to look like a reflection of the parabola. So we'll draw a reflection of the parabola here. And then when any one of these points is rotated around the x-axis, it's going to create a circle in 3 dimensions. And we're looking at a 2-dimensional graph, but we can kind of draw these circles here to get an impression of what it might be like in the 3rd dimension. So we have all of these circles that kind of get stacked up next to each other, creating this kind of cone-like shape. It's not quite a cone because the sides of it are not flat. They curve outwards. So the circles get bigger and bigger as you go to the bottom, faster than you would in a normal cone. The question then is, how might we calculate the volume of this shape? Well, our geometry formulas for cones are not going to serve us very well here because our shape isn't quite a cone and there's no way to cut it up into different cones. But if we think of it as a collection of circles that might present to us a way in which we could find its volume. Because if we imagine all of these circles being stacked up on top of each other, we could ask ourselves, well, what would happen if we found the measurement of each of these circles and then just added them all together? That would give us that full shape. Luckily, we know how to measure one of these circles. The measurement is pi times radius squared. And if you were to ask us to add an infinite number of circles up, we have a method for doing that as well. It's called the definite integral. So if I was able to add up from A to B the area of all of these circles, that would result in for me, the volume of this shape. The sum of all those circles is going to be the volume. So let's see how we might calculate this. Well, first, we would ask ourselves, well, where do we start our circles and where do we stop? Well, the first circle is at x equals 0, and the last circle is at x equals 4. So our definite integral is going to go from 0 to 4. And then we might ask ourselves, well, how would I find the area of any one of these given circles? So if I took this circle, say at x equals 3, what would its radius be? Well, its radius is going to be defined by this y-coordinate up here. That is the distance from the center of that circle, the center lying on the x-axis. Well, how would I find this y-coordinate? I'd come back to our original parabola. This y-coordinate is going to equal 1/2 times 3 squared, or 9/2. That would be true of any other point and any other circle that I choose along this graph. The circle is going to be formed by the y-coordinate being equal to the radius. And in every one of those instances, the y-coordinate is going to be calculated using our function, or in this particular case, 1/2 x squared. So that means if I want to find this volume, I'm going to do pi times our radius, which is 1/2 x squared, and I'm going to add up all of those circles. This gives us the equation that we can use to actually calculate our definite integral. We got 1/4 x to the 4th dx, and then we would just solve for here. The definite integral is going to be pi over 20 x to the 5th, and we're evaluating from 0 to 4. The 0 doesn't matter because that equals 0 when you plug it in, but we do want to plug in our 4. Pi over 20 times 4 to the 5th power. Let's just simplify this a bit. I'll divide by one of my 4's. 20 divided by 4 is 5. 4 to the 5th divided by 4 means 4 to the 4th. And we get 256 pi over 5. Turns out that this process is going to work for any shape that is rotated around the x-axis. We're always going to get a collection of circles. Those circles are going to be formed by spinning points around the x-axis, and adding them up using the definite integral is going to tell us of the volume of the shape formed. And so we can generalize this for any shape. If I want to know the volume of something that has been spun around the x-axis, well, that's the definite integral from a to b of the area of each of our individual circles. Or we can represent that even better by saying the definite integral from a to b of pi times whatever our function is squared. Adding up all of those circles is going to give us the volume of our shape. So here are two practice problems. I'd like you to try and sketch a picture of these rotated shapes and then use the way we have defined volume of rotations above to see if you can calculate what the volume of the shape that is formed is going to be. We'll talk about these two problems in class next time.